Welcome to today's Research Pays Off. I'm now going to hand it over to our speaker, Dr. Eshan to speak about the performance evaluation of MnROAD Reflective Cracking Challenge Asphalt mixes.
Thank you very much, Lauren, and hopefully everyone can hear me okay, and also the screen share has come through okay. So if it doesn't, just feel
Yes.
free to interrupt and I will try to reset it. So thank you for this opportunity to talk at the Research Pays Off today. For the National Road Research Alliance, I'd like to give you essentially use this time to give you an update based on the ongoing study on MnROAD Reflective Cracking Challenge, or MRCC, as it's often referred to as within the context of NRRA. In true spirit of NRRA, this is really a team effort where we at the University of New Hampshire are the primary contractor for this study, but it's really a joint effort between us as well as from Auburn University and National Center for Asphalt Technology and the Heritage Research Group. So I've listed people from all of these organizations, and obviously the actual origination of study, as well as the test cells, the material sampling, and also some of the testing effort is all through the Minnesota DOT and the MnROAD. So obviously both Michael Vertis and Ben Worrell have been very well involved with this effort along with the research team, which is us, Auburn and Heritage Research Group. Today's presentation really focuses on one of the tasks in the study, which involved sampling of the asphalt mixtures during the construction of these MnROAD test cells that are part of the MRCC project, and then literally using a kitchen sink type of approach with number of different type of lab tests that have been conducted on these, just to do a baseline comparison of these different type of asphalt mixtures. Obviously, the proof is in the pudding. So more interesting comparison would be when we look at the results of the actual cracking at the MnROAD cells, which is coming, and that would hopefully be the next webinar that we do. In today's webinar, I'll really focus on how different lab tests evaluated these different mixtures that were put down at the MnROAD cells. So essentially, the way I have this presentation formatted or organized is to go through just a quick overview of the MRCC effort itself, just remind everyone on what we are trying to do as part of this particular effort, and then go a little bit more into the actual tests. I won't go into every test result, all the details. I'll just try to summarize them. I won't be able to do it in the given amount of time if I spend too much time on each one, but also show you some of the mechanistic modeling results, since we have taken these test properties and put them through different type of modeling systems that exist, some more specific to reflective cracking, some just generally to cracking in pavements, and show how they compare these different mixed alternatives. And there's an important part to keep in mind here, that this effort is really overlapping with an ongoing national study on additives that may be used in asphalt mixture, especially those with plastics, rubbers, and aramid fiber. So MRCC effort is really a complementary effort to an ongoing study led by NCAT and MnROAD or MnDOT on additive group, where that's a separate pooled fund that's ongoing, and both of these studies use the same set of MnROAD cells as a northern experiment to that additive group study. So just reiterating the overarching objectives of the MnROAD Reflective Cracking Challenge, and those of you who have been involved with NRRA for some time may know this, that there's really a second effort from within NRRA on reflective cracking. The first effort, what I typically call the phase 1 reflective cracking study, was one of the original or the first projects during the phase 1 of NRRA that was undertaken, that started in 2017 and completed in 2021. And that effort really focused on providing some tools to mix designers and pavement designers regarding selection of overlay mixes and thicknesses of overlays when it comes to asphalt overlays on rigid or concrete pavements. This effort, the current MRCC effort, extends that by also doing similar things when we are looking at asphalt overlays on asphalt pavements. So here the primary focus will be, especially in many Midwestern states, what we call BOB or bituminous on bituminous type of pavement systems. In terms of outcomes, as was the outcome in phase one, we'd like to provide a decision tool to the users as an end product of this study, where they are able to really look at what would be your performance and life curves look like when you use a certain type of asphalt mixture with certain thickness on a given asphalt pavement that needs an overlay on it. And that is really done in terms of performance, is done in terms of measures like roughness. Also, there's a fair bit of sustainability assessment aspect within this project that will also provide some estimates of your embodied carbon contents and then obviously life cycle costs as well. So just to summarize the MRCC effort as a whole, this effort really relies on 10 different test cells or test sections that have been constructed at the MnROAD facility. All of these are on the main line on Interstate 94 westbound. And you can see where they are located at. And that phase one that I mentioned was really done on the original I-94 westbound alignment that I believe is getting ripped out right now or has already been as a part of replacing that. But that's where the old cells were from the phase one. This phase is on what is the main line right now, which means that they see a quite substantial amount of real life interstate traffic on it, except when traffic is diverted to the other lanes in order to do the data collection or maintenance type of activities. This just gives you overall cross section, so you can see it's a fairly built up flexible pavement system that's on the natural clay loam subgrade that we have at MnROAD facility. I'll go more detail into this top portion because that's where the differences between different cells come into play. So the way the study is designed, and again, it was really through the flexible team within NRRA as a group effort. Everyone pitched in and provided feedback into designing these sections. So it really started with what we have was the way these were built was initially building 5 inches of asphalt on top in 2 lifts with 2.5 inches each. A standard MnDOT 58 S minus 28 mixture was used. All the mixtures in this study are 12.5 millimeter or half inch. So that's the mixture that was used, placed in 2 different lifts. Once that was done, and each cell is about 500 feet long, so there's 400 feet of actual monitored or instrumented area just to avoid the transition areas at either end. Within that 400 feet, it was further divided into 2 portions. So you have a 200 feet portion, which is like your classical flexible pavement. And then the second 200 feet portion, what was done was after initial construction, transverse sockets were made within that section. And that's what is represented with these red lines. So you can see the type of socket. So you have initially a 25 feet spacing between these transverse sockets and then a 50 feet spacing. Now, in order to really create the most severe reflective cracking conditions, these sockets are full depth, as in all 5 inches of these asphalt pavement has been cut all the way to the bottom of that second lift as well. So they really are setting us up with these overlays to make sure that they're really getting tortured in a pretty severe way. And that's important because as with any research study, there's a limited timeline with this study, and we want to make sure that we get to near the end of life of these overlays in a meaningful time frame and don't have to wait 10 or 12 or 15 years to get to it. So once the sockets were done, the next step was to essentially go with a milling machine, and that really removed a top inch of this top lift of the top 2.5 inches, leaving behind 1.5 inches of that that initial asphalt with the socket in it for the half of the section. And then a 2-inch unique surface was placed. And it's called unique surface because each cell, that is the only variable. So between those two cells, the rest of the structure is identical. They all have the same type of layout as you see on the bottom. They all have the bottom 4 inches and everything below to be identical to each other. So what are these unique surfaces? There's 10 cells, 10 different mixes. So the first two are really controls, and there we are primarily comparing our standard unmodified asphalt binder versus modified binder, or if you speak the MnROAD lingo, then that would be your B oil versus C oil. So it's essentially comparing your two, which has or cell 20 to 30, which is this mix 2, which has your unmodified binder, and then cell 20 to 39, which has modified binder. Keep in mind that this 20 to 30 mix is also the mix that forms this bottom 4 inches on all of these cells. So that's your standard base mix there. Then we have the additive sections, and the first two comparative sections have aramid fiber. So they are made with that modified binder together with aramid fiber, two different manufacturers that you'll see on next slide. And really that's the main difference there with cells 33 and 34. Now, as it happens for the plastic and the rubber modified mixes, just starting off of that 58 minus 28 or minus 34 would result in those mixes getting excessively stiff very quickly. And so a 49 minus 34 unmodified binder was necessary to use those type of additive products. And since we were going to have a 4934 modified mixes, it was decided that we should also have a control section that's made with that same bitumen source, same binder source, as is used in case of your some of your plastic and rubber additives. So cells 36 and 37, 36 is modified with a dry rubber additive. 37 is modified with a 36 with dry plastic additive, 37 with a dry rubber additive. And then lastly, you have cells 32 and 35. And these are wet additives, which are typically the additive is reacted into the binder at the terminal rather than directly added into the mix, as in case with the dry additives. Also, if you recall in the phase 1 of NRRA effort, there was one trial with a SuperPave 5 mix, and that had done quite well. So that was considered here as well. So the cell 31 here is essentially a 58V minus 34 modified binder using SuperPave 5 design approach, and that's your 10th cell. Now, keep in mind that these first 9 cells are also directly shared with the additive group experiment, so they are providing data to both studies, and that's why there's this parenthesis NRRA for cell 10, because this one is only unique to the MRCC effort. Someone had posted about the wrap content, so all of these mixtures have 20% wrap in them, and single wrap source that's used on all of those. All of these have same aggregate sources. Everything else is very, very similar or comparable between them. So here you get a little bit more insight into what is the difference or how those additives come about, who manufactured them and stuff like that. So the wet plastic is essentially using a very low density polyethylene plastic at 1% dosage together with alloy to make the wet plastic. The two aramid fibers, one is the ACE fiber by Surface Tech, and you can see the dosage rate 3.4 ounces per ton. With Forta fiber, it's 1 pound per ton of asphalt mixture. So those are the dosage rates on those. Again, dosages were primarily based off of the manufacturer's recommendations. And for the additive group mixes, they were also mixes that were designed using BMD approach by NCAT, by Auburn University, where they had to meet a certain threshold. So more details you can find in the additive group pooled fund website. They actually have all the details on the mix design and how the mixes were finalized and so on. The wet rubber has about 10% by weight of binder as the rubber additive. With dry plastic, it's again the LLDP pellets that were directly added at 0.5% dosage by weight of aggregate, so quite a bit of that in there. And then dry rubber used the product called Smart Mix by Liberty that is added into the mix as well. So for today's presentation, as I said, we cannot go through everything. And so I've tried to limit it to just the lab test results and the mechanistic modeling predictions that we have to date. Lab test, again, many acronyms here. We did many type of testing in order to really capture a breadth of different test procedures that are right now available and are being used by many agencies, many NRRA agencies. And also we wanted to have some baseline information that we can use in models such as complex or dynamic modulus and so on. Also keep in mind that all testing was done with at least two different conditions. One is just a reheated condition, and one is a condition that is often referred to as critically aged condition, which for this location, based on the cumulative degree days, would be 6 hours at 135 degrees Celsius of loose mix aging prior to compaction. On top of that, for the Illinois Flexibility Index test, Illinois DOT conducted that test. They also did what is their default as part of their BMD and mix design acceptance approach, where they actually compact or age their compacted, finally prepared flexibility index test specimens. So they also did that long-term aging in addition to these two conditions. So you'll see those results as well. So quick summary of test procedures itself. Complex modulus, we followed the AASHTO T342 test protocol where the testing was done at 3 different temperatures, and at each temperature we have 6 testing frequencies that allows you to really generate the master curves of your complex modulus or norm of complex modulus, which is dynamic modulus, and the phase angle. And that's important because we need to have that parameter in order to do different type of modeling where we can simulate the properties of asphalt mixture, its response at different frequencies and temperatures with different traffic speeds, with different climatic conditions, and so on. From cracking perspective, there's one parameter that has been often explored. That's a rheological parameter. Now, oftentimes you hear this in context of binders called Glover-Rowe parameter. There's also an equivalent of it on the mix side called Glover-Rowe mix parameter. So we were able to calculate this parameter using the complex modulus test results, and I'll show you those. In general, this parameter indicates how stiff is your mix, as in how much stress it will generate when loaded, and also how quickly it can shed its stresses through creeping or relaxation processes. And so typically we want a lower value for this parameter in order to have a better cracking resistance. So when you have a lower value for this parameter, usually that means that that mix would have a better cracking resistance. CT index or ideal CT, again, quite popular test nowadays with people trying it out for balanced mix design applications. And I won't again go into too much on this test because I think most people in our community are quite familiar with what this test is, but it's essentially measuring overall bulk response of your mixture when it's loaded as to how it will break apart or how it will dissipate the type of total energy that's put into the specimen. And so you look at the total area under your load displacement curve, and you also normalize it using 2 parameters. One of them is really looking at how quickly your material falls apart, and the other one is looking at just how much of strain or how much of deformation your material can undertake. So you have L and M parameters. Fracture energy is just taking into account the area, and then you also have thickness of specimen to normalize against different thicknesses. So typically for this index, you want a higher value that would indicate a better cracking resistance. Illinois Flexibility Index Test or IFIT, again, there's AASHTO standard for it. Similar in concept. So here the main advantage is it's truly a fracture mechanics driven test with a notch unlike CT index where you're just looking at overall breaking susceptibility of your mixture. And typically, once again, you want a higher value to get better cracking resistance. It's once again looking at that area under your load displacement curve that represents the total work it takes to break the specimen, but also it pays attention to how quickly the crack travels through the specimen, what's your crack velocity, and that's done by looking at the slope on the post-peak side to get your composite index called flexibility index. Now, as with CT index, all of this testing was done at 25 degrees Celsius in this particular project. Um, Cyclic fatigue test. So this is a test procedure that Federal Highway Administration has developed and matured with efforts from North Carolina State University. So it's a test procedure that's really designed to look at how your traffic loading will degrade your mix integrity or mix capacity. So it's really focusing on that fatigue phenomena. And the testing is really done by using your a cylindrical specimen similar to a complex modular specimen that are glued on top and bottom and then really imposed with the cyclic loading. So you are applying a cyclic straining of on that specimen and really looking at how the capacity of material degrades as you constantly apply a fixed amount of straining onto that specimen. So there is again a damage-based index that has been proposed, and Federal Highways has conducted a validation of this index, and it's called S apparent or SAP, as oftentimes people refer to as. So with this index, once again, typically you want a higher number to have better fatigue performance. But keep in mind that this is a reflective cracking study. While that's the case, half of these cells, the first 200 feet of these cells, are really designed to be a traditional flexible pavement. There's no sockets or no joints underneath. So that's where a parameter like that really makes a lot of sense, because you're really looking at just classical fatiguing of that structure under traffic loading and seeing how these mixes may perform differently. Overlay tester. So Texas overlay tester, again, developed and used by Texas DOT through efforts of Texas Transportation or Texas A&M Transportation Institute. Also another test at room temperature conditions. And the idea here is again, somewhat of a simulative test procedure where you have your test specimen that's glued to these metal plates with a joint in them, and then those plates open and close in order to really form the crack as it travels through this specimen. So it's really a simulative test to look at reflective cracking, and then there's typically two phases within this test. You initially see a phase where there's a quick drop in how much force is needed, and that's your crack initiation phase, and then there's a growth phase where that crack continues to grow with time. And so there are parameters like CFE and CPR. CFE is really indicative of how much is the potential for your specimen to what kind of energy it would take in order to get that initial cracking to happen. CPR is simply looking at, with each repeated cycle, how much more that crack would grow. So there's again an index or index parameters that we can extract out of this test. Now, keep in mind that with MnDOT or MnROAD, we are at a cold climate location. All these tests that I talked about until this point, especially the cracking tests, they are all done at intermediate temperatures. And that's great when you are simply looking at general response of mixes, especially in warmer conditions. But at a low temperature, you obviously need to know what type of embrittlement these mixes would undergo as things cool down. That's one part. The second part that we would also need to know is what happens to these mixes just under the thermal action of cooling, right? Because if you recall that all of these pavements, whether they have joint underneath or not, as winter comes and as temperatures drop, they are going to try to strain because of thermal shrinkage, and that will really do two things. One, it will generate tremendous amount of thermal stress or tensile stress in the asphalt mixture, but it will also make these mixtures lot less ductile or less tolerant to strains, And as a result, we need to make sure that these mixes can survive those low temperatures and do not undergo with cracking. I mean, just one point that I'll mention is phase one of NRRA effort on reflective cracking clearly showed that thermally induced reflective cracking, when you have very low temperatures, as a result, low fracture energies in asphalt overlays, together with that underlying joint opening because of the thermal shrinkage, was much more severe condition in resulting of cracking than just the general traffic induced reflective cracking that you may see at room temperatures or at warmer temperatures. So extremely important to look at low temperature characterization of these properties. Um, Again, the purpose here is to look at how the cracking resistance changes at low temperatures with reflective cracking conditions. Now, as with other tests, right now there's ongoing efforts to also look at additional parameters that we can get from this test just beyond the energy. Again, that's ongoing effort under development. So for this presentation, I've limited to just presenting fracture energy for this shape compact tension test, but please be mindful that in future, once those other parallel efforts have matured and we have other indices, we may have additional indices that may be presented for this test as well. And then last but not least is the uniaxial thermal stress strain test. So the idea here is not to necessarily have a fracture test or a cracking test, but to have a better understanding of what generates the stresses in our asphalt mixtures when you cool them down. And to that effort, or effect, a test procedure was developed at University of Nevada, Reno, called UTSST. Many of you may know of a TSRST, which is somewhat similar test where you have a prismatic sample of asphalt and you are just straining it. Here, the advantage is that you really have companion samples. You have a restrained sample, but you also have an unrestrained sample. So not only you are getting your stress history of what happens to asphalt mixtures as you cool it down and you don't let them freely shrink, but you also get your strain history to look at what happens to your asphalt mixtures. If it was unrestrained, how much would it shrink with temperature? Combining that stress and strain history, you are really able to look at what's happening in the evolution of that mixture in terms of how it generates the stresses, at what point it starts to fail, not like a fracture test with a notch, but fail internally, as in how the stresses get so high that material is starting to get damaged throughout, and start to break, and eventually this restrained specimen breaks or fractures into two pieces. So using that information, we are also able to extract some parameters that can allow us to tell about how these different type of mixtures may behave when it comes to thermal shrinkage or when it comes to low temperatures. So there's another test that we set up and conducted on these mixtures. All right, so now with all of these test results, let's start to look at different tests. Let's start to look at the results themselves. Now here, what we are seeing is simply just looking at on a black space, which is really a plot of your dynamic modulus and phase angle, just at one temperature and one frequency. I just wanted to show you the effect of aging. Okay, so 10 mixtures here. Don't worry too much about which symbol represents to which mix type. We'll come to that later on. The main point I want to make here is that aging is important, because what you are seeing is each of these black or solid dots has a companion hollow dot. So this for one of the mixtures, this is for another set of mixtures. And what we are seeing is as we age these mixtures, two things happen. They stiffen up. So as we go from hollow to solid, it's representing or representing short-term or unaged condition, just a reheated condition, to aged condition. So they get stiffer, which makes sense. But also equally important, they become less relaxant, right? Asphalt mixtures are viscoelastic, which means that when I strain them, after time, the amount of resistance or stress generated in them is really degrading or decaying. This horizontal axis represents how quickly these materials are able to shed those stresses. And we can see that their capability to shed the stresses is retarding or reducing as we age them. So bottom line, aging really important when we are trying to evaluate things like cracking. Now, in terms of parameters, so as I said, there's one parameter that tells us rheologically how these mixtures may perform, what type of stress they generate, what kind of capacity they have to relieve the stresses. So um, if we look here, we want a lower value. Lower value represents a mix that would have less stress generation and better ability to shed those stresses. So right away, we can see that the control mixture has very high values compared to all of these modified materials, whether it's just using a very soft binder, using a SBS modified binder, using plastic additives, rubber additives, or fiber additives. And keep in mind that both of these fibers essentially use the same mixture, same binder, the 58H minus 34. So the 20 to 39 is comparable to 33 and 34 in that context as well. So what we are seeing is that the control mixture 28S minus 28, 58S minus 28, quite high Glover-Romex parameter, which means it has reduced relaxation, increased stiffness. The fibers, the dry rubbers really showed good relaxation. They had a high phase angle. Dry plastic did stiffen quite a bit after aging, so we can see that effect as well. So if we see the comparison between green bar to red bar, how much has the change? So you can see that the dry plastic was quite age susceptible as compared to some of these other mixtures. So those are some observations just on a rheological scale. In terms of the ideal CT or CT index, so once again, two set of bars for each of these mixtures. Green represents the reheated plant mix, lab compacted. Red represents aged plant mix, lab compacted. So it went through that 6 hours of loose mix critical aging at 135 degrees Celsius. And what we are really also comparing, since there are so many different agencies are using this test, there's many different thresholds that different people are using. So I just tried to put these three lines as sort of comparison. Don't pay too much attention to them because depending on which agency you talk to, some of them use threshold of 70, some of them are using threshold of 45. So there's different thresholds out there and different entities are using different values. But what we can in general see is that once again that control material without any type of modification had the lowest CT index values, both especially unaged or reheated. And with aging, it also had a low value. The only other mix that actually had very low value or even lower value than control was Super Pave 5, even though it used that 58V minus 34 binder. It did not really have that high of value. You can also see that some of these other mixtures did degrade quite a bit. The ACE fiber here, the dry rubber, and also wet rubber, all of them had a very high age susceptibility as determined by this mixture versus some of the other materials like the 4934 control. There's barely any change after going through that aging cycle. IFET or Illinois Flexibility Index test. So as I'd mentioned earlier, there's three set of columns here. Okay, so the first one is again reheated. Second one is the standard NRRA agreed upon aging condition, 6 hour loose mix, 135 degrees Celsius. And then the third bar is what Illinois DOT is using for their long-term aging for IFIT testing, where it's essentially aging done for multiple hours at 95 degrees Celsius on a compacted flexibility index test specimen prior to testing. So you can see the third set of bar. Right away, you can see that that third aging level is the most critical. It has the most drop, which also doesn't make it does, which also makes sense because it's also longest aging condition compared to the other conditions. So it is more severe. The other observation I saw is that there was not really too much distinction. So in other words, if a mix had a certain amount of drop going from reheated to the critical aging, that mix continued to degrade further with the Illinois DOT's aging procedure. So there was no discrepancy, in other words, where a mix all of a sudden did not show as much of aging related degradation with that more severe aging as it had done with, let's say, an intermediate aging. So that's good because they are all consistent. Once again, the two mixes that were the lowest properties are the control mixture and the super pave 5. All the other ones, I think statistically, they, at least in unaged condition, are very comparable. And also in aged condition, there wasn't too much of a difference. One thing that we did see was that the amount of drop uh, that we saw from unaged to aged was a little bit lower on the 58H minus 34 and wet rubber. They did not have as much of a drop. The other ones continued on similar trajectory as that went from first to second aging condition, then second to third. Also, I put a line here at 8 because that's oftentimes a threshold that Illinois DOT is utilizing. Now, keep in mind that's typically done for unaged conditions. So all of these were already exceeding that threshold in the unaged or reheated condition. And some people have shown 5 to be threshold after aging, and most of these still exceed that threshold of 5. Cyclic fatigue. So as I said, we'll just use one parameter here, the SAP parameter, which Federal Highways is proposing and recommending. There's actually a info brief from Federal Highways that also gives the limits. And it uses same kind of criteria as the MSCR binder grading, where you have your standard heavy, very heavy, and extreme traffic levels in terms of millions of easels that this roadway might be experiencing. Since there's tied to fatigue cracking, it makes sense to have the limits tied to the traffic levels. As you can see that all of these meet and exceed the standard. Most of them get to the heavy as well, which would really be the case with the traffic levels that we are seeing in this particular case. So that's the threshold of 24 corresponding to 10 to 30 million easel type of loading conditions. And most of them retain that even after aging. Once again, the clear distinction is the control. Control was always substantially short falling value as compared to almost all of these modified materials. The Super Pave 5 and the 4934 were the only two which, after aging, did have a appreciable drop in their properties as well. Overlay tester. So again, there's two parameters that you can extract from overlay tester. You have what is called the CFE, which is your resistance to crack initiation. Excuse me. Here you essentially want a higher value in order to have good performance. And unlike all of the other parameters that we saw so far, really the control was the one that had the highest value here, which also makes sense because this parameter is really telling you how much force it takes for that crack to get going. And when you have more stiffer mixture, it gives you a higher value. So we are seeing that aspect here. And that's why with aging, all of these parameters exceeded as compared to their unaged condition. To me, more interesting is really the second parameter that we get from overlay tester, which is your growth rate. And there you want a lower value because you want a slower crack growth. You don't want a fast crack growth. And there you can once again see that after aging, all of these mixtures have a faster crack growth, which makes sense. Except some of the mixtures are more resilient. And keep in mind that these last two with the fibers, they show quite a bit of resiliency to this. Not surprising in this test setup at room temperature, because those fibers are really going to engage and provide the bridging action against your crack development. So they are carrying some of the load, preventing that crack from growing. And that's why you are seeing this relatively flat value with a low CPR values. With more of your traditional mixes, you start to see them creep up as you go through aging. And once again, the control was the one with the lowest performance or the highest crack growth rate. as we saw with other tests. The dish shape compact tension test fracture energy values. So I put just a line as a reference at 450 joules per meter square, just as a reference line there, because that's the value that has been used in past, also for designing mixtures in cold climate conditions with this particular test and this parameter. So as we can see that the control actually failed to meet that initial threshold. All the other ones well exceeded that. And as expected, after aging, most of them saw the drop in that as well, with the only different ones were the ones with the rubber. So from low temperature perspective, it seemed that these mixes with rubber, they were really retaining their ability in order to absorb the energy even after having gone through aging, as opposed to other mixtures which were seeing almost a steady decline as they go through the aging condition. So what we saw is that the dry plastic, dry rubber showing relatively less drop after the aging. The wet rubber obviously showing very good properties and even seeing a slight increase after aging versus some of the modified one. Obviously, control was already below the threshold, but even the 58H minus 34 as well as Super Pair 5 both showing a appreciable decline in their fracture energies after they had gone through aging. The uniaxial thermal stress strain test. So what I'm showing here is really a temperature, two temperatures, one temperature which tells you when your material starts to behave more glassy, where it's starting to lose its capability to easily strain and also recover back from applied stresses. And then the second is when it's typically expected to crack, at what temperatures, assuming the cooling rate that this test uses, and so on. Now, all the results here are for aged mixtures only. So the green and red doesn't mean short-term or long-term age. Green just is the glassy temperature. Red is the crack initiation temperature. Just to make it clear, I put the grade lines. So those are your standard Super Pair PG low temperature grade lines at minus 16 and then 6 degrees thereafter. So as we can see here, in general, the two fiber modified mixture showed the lowest cracking temperatures, or temperatures that they could survive before there's initiation of crack. Also, the dry rubber showed quite good properties. So did the polymer modified 58H minus 34. The standard did not show or the control did not show as low of a temperature for cracking. Although it's graded as minus 28, we are not testing binder here. We are testing mix, and we are testing at a certain rate. It actually showed about minus 22 Celsius when it started to undergo crack initiation. So that's really the summary of all the different tests that we did. And I recognize that we are almost running out of time, because I want to leave some time for discussions as well in case people have questions. So what I'm going to do is, for the mechanistic modeling, I won't spend too much time. I'll just jump to the key results and then summarize my presentation. And if anyone has more questions, they are welcome to contact me, and I'd be happy to discuss with them the results and so on. So three type of simulations that we did. First one is just the pavement ME, and I'm just going to show you the key results here. What we are looking at is, in conducting ashtoware pavement ME analysis, what we are looking at, what amount of reflective / thermal cracking may develop in these sections in terms of feet of cracking per mile of or lane mile of your pavement length. And you can see it after 1.5 years and 24 months, we had to play with traffic to really get it to crack in that kind of duration. In general, what we are seeing is that the control is again actually showing not as poor or of properties as some of the modified mixtures are, but that's also an artifact of how pavement ME works. It does not see or use any of your cracking results or indices. It's purely driven by your complex modulus. And so it's really a good demonstration, again, to show that when it comes to things like cracking, especially reflective cracking, tools like pavement ME may not be as reliable, especially when you are doing some of these more innovative asphalt mixtures that are not like your traditional asphalt mixtures. When you look at traditional asphalt mixtures, as in these three, especially 58H, 34 minus 58S minus 28, then it makes sense where a polymer modified mixture usually shows no cracking when you have some cracking in control. When control is almost fully cracked, there's still less than fully cracked in this case. But when you look at rubbers, plastics, or fibers, I don't think you can really trust the pavement ME results. And so that's where we also looked at another tool called Texacol, which is developed by TTI. And this uses the overlay test as an input, and it actually simulates your fracture mechanics based crack growth. So if we look at the results from that tool, now we can start to see a little bit more alignment with what our lab test told us. So you have your control. What we are looking at is what percent of your underlying joints or cracks have reflected through. 100% would mean every joint has already gone through. And you can see control had very high amount of cracking already by the time you went to 12 months. We already had about 90% of those joints reflected through, versus if you look at some of these more modified mixtures or mixtures that have fibers or plastic or rubber additives, they are performing better. You can see a slower rate of crack growth as well in those cases, with results for example, for this fiber product, it had the best performance even when the most of the other mixtures controls had started to get to 100%, you were still well below that cracking amount. And then last tool that we used here was FlexPave, which is again a tool that's promoted by Federal Highway Administration. It's actually trademark of USDOT and Federal Highway Administration. It's more looking at cyclic degradation, so it's not designed for reflective cracking. It's more for damage from repetitive traffic and thermal cycling. And there also the results align a little bit better with your test results, lab test results, where control showing again a very high damage potential compared to other mixtures. If we just focus on near the top, because that's where the uniqueness is in these different mixtures, and that's where you are seeing the most of the thermal action as well. So you can see again a polymer modified mixture doing quite well with substantially lower damage compared to your control, and then a different type of additive showing different responses depending on the type of additive. So I apologize again that I went through that the modeling part very quickly, but just with interest of time, I didn't want to. I wanted to make sure that there's few minutes left at the end for me to respond to any questions or comments. So key observations. In this experiment, additive treated mixtures all outperform control mixtures, and by additive that also includes things like your standard SPS polymer modification, as well as with those with plastics, rubbers, and fibers. Amongst the controls, that C oil, the 58H minus 34 substantially outperformed the unmodified one, and that's not a surprise. Within the treated mixtures in general, the rubber and fiber modified ones exhibited better performance than those that were treated with plastic, but that also you have to take it with a grain of salt, because that depends. We had two type of plastic products, and the dry plastic was the one that consistently underperformed compared to most of the other products. And then lastly, between different mechanistic models, if we compare the results of these different indices, whether it's the fracture energy from DCT or flexibility index or whatever you may have, where we saw the most consistent matching was with the Texacol simulation system had the best alignment between the performance test indices and the lab results. Now, keep in mind, all of this is synthetic in the sense that we are only comparing models to test result properties, not the field performance. So that's the next step. The next step is essentially, now that the MnROAD cells have started to crack, this January was the first time that we observed cracking. Not surprising in the control section with 58S minus 28. Now that data is coming in, we are actually able to compare the field performances to these indices to tell you which lab test makes more sense or gives you a better comparison, but also which modeling efforts can be more reliable in order to predict the performances when it comes to reflective cracking. So obviously that is effort that's undergoing right now. Also, part of this project is doing quite a bit of LCA or life cycle assessment work. Phases A1 through A3, what we call cradle to gate, is completed. That I presented this already to the many of you who were at the NRRA workshop in beginning of May, I think. So you already seen those results. The A4 through A5 is already, the analysis is done. We are in the report writing phase. And then once we start to have the field performance data, we will also be able to get some of the B2, B4 type of life cycle phases and their impacts and cost as well. So bottom line, there's still a lot to come in this study as we start to integrate lab results with field performance and performance modeling as well as LCA. But there's already so much that we have learned between how these mixes are expected to perform just using these lab test results that I showed you today. And just last but not least, a picture. You can see two cells. This one is the 20 to 30 cell with the control section. Nice big reflective crack there. We know it's reflective crack because you can see the sign here. Prior to overlaying, the location of each underlying joint was marked, so we know exactly where there's underlying cut. So we know it's reflective cracking, and then you can see a companion section. This one is 20 to 39, I believe, with the SPS modified. Cracking in shoulder, but there wasn't a cracking in main line at the time this picture was taken in April. So with that, I'll stop, and hopefully if people have any questions or comments, I'd be happy to try to answer those.
Well, thank you, Eshan. I do believe you answered the question that was in the chat about the
Recycling.
material. Yeah. So that is all I've seen so far. If anyone has any other questions, you can raise your hand, unmute, type it in the chat. I do see a question here. Did you need more asphalt to coat the dry additives?
Good question, Kurt. And yeah, so for the dry additives, and we have the mixed designs. If you go to actually the NRRA project page, the construction report is there that has all the mixed volumetrics as well. And the answer is no. So the dry additives did not really end up with any additional binders, at least for the dry plastic, to get them coated. Keep in mind once again that this being a companion effort with additive group experiment, essentially we also had the way the mixes were optimized initially were by doing balanced mix design, testing using Hamburg and CT index in order to get them to a certain minimum CT index and passing Hamburg numbers. And so there were some modifications done on the basis of that. But also that's why you see those dry additives have such a softer initial binder grade in order to activate them. But as far as my memory serves, there was not really additional binder needed or added, at least not in appreciable way for those dry additives.
Any other questions or comments?
Relative cost of each of these grade. Good question. To come. So we actually did obtain or gather that data in order to use it within the LCCA. So the life cycle cost analysis will actually utilize that. Obviously, on this particular project, the additives were donated for free by the respective manufacturers, but we have not fully processed the information. We have the data, and that will be used within the decision tool when we are doing the life cycle cost calculations in order to look at it. Just in a quick way, there's really between the SBS modified and the regular, there was your standard difference that you typically see in your state based off of your modified binder PMB versus your straight run binder. But yeah, for these other products, there's obviously cost that is attached to them, especially products like fibers. There's a standard cost in that, and that will be included. We are working on the task 4 report that has the LCA, including the cost, and that will be included in that.
Thank you. This is our final call for questions. Oh, all right. So the opinion of sawing HMA when overlaying a new or nearly perfect condition and filling immediately after paving in an effort to control secondary cracking and damage from incompressible particles and moisture.
So personally, I don't recommend sawing HMA when overlaying a new or nearly perfect condition. I would not do that. Here it was done more out of necessity to create that really severe condition underneath. Now they did do some air blowing after cutting these and really brooming to make sure that there was no debris that was stuck inside these sockets in order to prevent make sure that you didn't end up with incompressible particles in there. But again, the idea was to create the most severe condition where your underlying pavement has like a full depth cut or crack in it. Personally, my opinion would be to not do that. Any benefit you can get from any sealing action that's still left behind in the underlying overlay, together with any load transfer that you can get from, I would take it. That said, I would definitely be suspicious if there's a lot of water coming through those underlying cracks, or if the cracks have really tented and there's a lot of loose material. I would recommend milling it until you get to a more sound layer prior to overlaying. So that would be my recommendation to prevent that damage from incompressible particles or moisture.
All right. Well, we have 1 minute left, or less than a minute. So I will adjourn us for today. And Eshan, thank you for your time. And thanks for the questions here at the end. And we hope to see you next time. We don't have anything actually lined up for July quite yet, but I do have something potential in the works. So we hope to see you next time at Research Pays Off. Thank you, everyone. Have a great day.
Thank you all.